This is the video solution to the example problem involving energy. So in this problem, I know the person, I'm going to figure out what the speed of the person is running at the bottom on the ground, and they're going to swing up 2 meters, and they're going to have a speed at the top of 1.5 meters per second. To begin with, when I'm looking at this, I've got velocities and height, so that kind of indicates I have kinetic energy and potential energy to work with. So I'm going to use conservation of energy. And I'm going to indicate that to my reader by saying sum of the energy at the bottom equals sum of the energy at the top. Notice the subscripts after the E, so that tells the reader where the location is that I'm considering. So that's important to have it there. All right, now within this, I'm looking at two energies, kinetic energy and potential energy. So I'll look at the kinetic energy at the bottom, the potential energy due to gravity at the bottom, the kinetic energy at the top, potential energy due to gravity at the top. Set up my equation, energy is conserved, so I'll have all the energies equal to each other. And then I'll go through and I'm going to ask two questions about the energies at the bottom, two questions about energy at the top, and that'll help me to create my equation. And these are the two questions we're always going to ask. First off, at the bottom, is the runner moving? And the answer is yes, it is. So in my next equation, I'm going to keep the kinetic energy part. At the bottom, is it above the other location's height? No, it is not above the other location's height. No means zero. So there's no height, so there's no potential energy due to gravity comparatively at the bottom. Now let's look at the top and ask the same two questions. At the top, is the person moving? Yes, they're moving at 1.5 meters per second. So I will keep kinetic energy. At the top, are they above the other location's height? Yes, they are. It's a difference in height. So I will keep that potential energy as well. So this gives me the equation 1/2 mv squared at the bottom equals 1/2 mv squared at the top plus mgh at the top. Now something nice happens mathematically. I've got the same object at the bottom and the top, so I have the same mass everywhere, and m is in every expression. So the m's will actually go away. They're going to divide out. That leaves me with 1/2 v squared equals 1/2 v squared at the top plus gh. It's very tempting to mark out the 1/2 v squareds, but they're different. The one at the bottom uses the velocity at the bottom, and the 1/2 v squared on the right-hand side uses the velocity at the top. So it looks like they're the same, but they're not. Now let's isolate v. I'll multiply through by 2 and take the square root. So that gives me the velocity at the bottom, where the ground is, to be the velocity at the top square, or the square root of the velocity at the top squared plus 2gh. Put in my numbers, do my math, and I get that at the bottom I need to be running 6.43 meters per second. That's something that should be doable by most people.